and other biofuels. So today the real LCA analysis, the practical part, you can say, it is starting. And today our guest faculty will be starting with inventory analysis. So this is the major, you can say, part or a major thing in LCA analysis, and try to learn the inventory analysis part in one of the initial part, important part in LCA analysis, and have your queries cleared from our guest faculty. So I invite Professor Jermier for the today's talk on inventory analysis. Yeah, please welcome.
Okay, good morning, everybody. So today we are looking at the part of life cycle assessment about the inventory analysis, which is really the key part of life cycle assessment, where you really have to make a careful and clear description of the technical system you are analyzing. And at least you start with the goal and scope, and then see which system you need to fulfill the goal and scope, and to be also clear on the functional unit, that you really create a functional unit that you're interested in, and which is also the basis to compare it to other systems. And at least generally in the inventory analysis, everything is mass and energy balance, so to say. So it's really based on the physical principles of things going in and things and materials are coming out. What are the inputs? Of course, you can put in materials, raw materials, or intermediate materials. You put in energy, could be heat, could be electricity, and any ancillary inputs, smaller amounts of materials, chemicals, or masses. On the other hand, of this mass balance, you have the outputs. Of course, you have outputs are the products, or in between the intermediate products. Yeah, this is the thing you're studying, you're interested. Beside, there could also be some co-products that are somehow relevant in the overall production process, where then you have to apply any allocation. And waste, at least waste is really something that cannot be used furthermore. And normally people say a thing is a waste if you have to pay to get rid of, because normally for waste treatment you have to pay, and this is sometimes a possibility to see if it's a co-product, a residue, or really a waste you have to get rid of. And then we have the different releases, so at least the substances going in the environment, which is mainly going to air, going to water, and going to soil. And we will see later on in the next lecture there are also other environmental aspects that might be of some relevance. We've seen yesterday, if you build up a process chain starting in nature and ending with your product, you have these different so-called unit processes. Yeah, the unit process, your system is split up in the main unit processes, and for each of these unit processes, you have to know what's going in and what's going out. And in the horizontal way, so to say, you normally put in the materials, what is the main input material, what is the main raw material, what are ancillary materials and services, what is the energy you need, and any other other inputs. And on the other side, on this horizontal side, are the products coming out, the byproducts coming out, and of course the releases to air, soil, and water. But as in LCA, you also have to deal with the construction of these unit processes and with the end of life. And this is the vertical part. Yeah. So at least in the upper part, I think, yeah, the upper part is at least what you need to build the process. Yeah? So if you build the bioethanol facility, you have to build it. You need steel, you need concrete, and all the elements. And at least that also for you have to know which materials you need to build up the process, even how much space you need, all the facilities. Um, then in between, the horizontal one is at least describing the operation phase of this unit process. And finally, LCA is also covering the end of life. Yeah, and sooner or later, an ethanol plant or a vehicle or a power plant is at the end of its life, and then it has to be decommissioned. And there you also have to see which of the hardware can be reused, which of them can be recycled, or what is really a waste or a residue or a contamination. So at least for each of these unit processes, you have to think about producing the facility, operating the facility, and dismantling the facility. And this is at least the key part of this inventory analysis. Um, as I've shown you before, it's the construction, the operation phase, and the dismantling phase to at least define the system that gives you the product and services. Um, what are the key outputs relevant for LCA? Yeah, as I've mentioned before, there are emissions to air. They are normally gaseous emissions. It could be CO, CO2, NOx, particle matters, SO2. There's a very long list of possible substances that can be released to the atmosphere. Yeah? And at least for these unit processes, you have the information. Yeah? If you have a combustion there, if you have a conversion there, where you know which of these releases are going in the atmosphere, and in the inventory analysis, you really have to put numbers on it. Secondly, you might also have liquid emissions, mainly going to wastewater, but also if it's only cooling water and you get rid of the cooling water, is also part, but at least all the liquid emissions, yeah, you also have liquid wastes. And finally, also solid waste. So all the solid substances, the ashes from combustion or from any conversion process, there's also solid waste that really has to be counted and quantified exactly for this unit process. Additionally, there are other things, for example, noise. Yeah? So if you have a heavy activity in that unit process and it makes noise, which is at least a very specific LCA. There are also LCAs assessing noise emissions or odor emissions. Yeah, if you're handling manure or other substances, you might create an odor, or even radiation. If you think on nuclear energy, any type of radiation could, I would say, in specific cases, also be of relevance if that is part of your goal and scope. Um, at least in a normal LCA, you don't have to cover all the substances. At least it really depends what is the goal and scope of the analysis that determines which information you need on each unit process level. So if you're only interested in the greenhouse gas emissions, you only have to consider here really the greenhouse gas emissions. If you're interested on SO2 emissions or particle emissions, so it really depending on the goal and the scope. And it's not the case that in LCA you always must cover all impact categories. No, it really depends on what is the question, what is the goal and scope. And for these, you have to make the inventory analysis. Secondly, on the input side, it's also relevant in the inventory analysis to count things that are going in. For example, the area. How much space, how much area do you need for the specific units? For example, in agriculture, if you're cultivating corn or wheat, of course, you have to know how much land you need to produce the amount of grain you need in your bioethanol facility. Yeah, and even this area, you know the yield, and with the yield, you can calculate at least how much area you need to provide the raw material for your system. Secondly, also the different resources, the different materials you need, the concrete, the steel, and all that is also something you can at least count on, and you can quantify, and also the primary energy. So how much energy you need to run the system, to build the system, and to dismantle the system. For the primary energy, on one hand, it's part of the inventory analysis. Later on, we will also see it's also one of the impact categories, describing the energy efficiency of the overall system. So still, the inventory analysis is really based on physical principles, at least covering a closed mass and energy balance. Whereas later on in the impact assessment, we see this is not only based on pure physical principles, there are also many assumptions or modeling behind it to come from a emission to a possible damage, but this will be in the next lecture. Then, of course, for the very beginning, uh, when you start to build up your system, you've seen yesterday, there's always an arrow in from goal and scope going back to the inventory analysis to the impact assessment. So it's always an up and down. So when you build your system and your unit processes, you always have to reconsider: am I still in line with the goal and scope? And here, at least, you have to really describe the system you're analyzing. Yeah, but it's also relevant in which country, even in which geographical location your system is taking place, because the yields on an agricultural area are very different from climate or from region to region. So you really have to specify in which country, in which region you are, to really cover the appropriate geographical scope. It's also relevant to describe in which year, because there are LCAs judging about activities that happens in the past to see if it was an improvement of the environmental situation. But there are also LCAs for today or even for future, saying, okay, if you want to make lignocellulosic ethanol, maybe the year will be in 5 years or in 10 years. So even there you have to describe in which year your analysis is trying to answer questions on environmental um, impact. And then in the goal of scope, of course, you have to define this function or describe the product. We've heard about the liter of milk. We heard about the driven kilometer. We heard about the emissions per kilowatt hour of heat or megajoule of fuel. This is really the function and the functional unit that really has to be described properly. I once saw an LCA on a beverage, on a cold beverage, and it makes a difference if you look on a cold beverage. For example, Coca-Cola is better you have in cold, or if it's at normal temperature. You really have to be very precise what is really the function, and it makes a difference if it's a cold beverage or a warm beverage, if it's a coffee or it's a Coca-Cola, because you also need energy to cool the product. And the interesting thing on the cold beverages, in most of the cases, the cooling system on the very end, before it's bought by the consumer, might be a very big impact, because the cooling needs electricity, and depending on where the electricity is coming from, for many beverages, this is the key element. Like for the coffee, it's the heating of the water, and for the tea, it's the cooling for the drink. So this functional unit really needs your attention to describe that properly. Then defining the system boundaries. System boundaries at least are defined: nature on the top, product on the bottom, and in between all the unit processes that are relevant. Already in the goal and scope, when you discover some co-products or byproducts, of course you have to be aware that you need an allocation procedure to be considered, or even to be reconsidered during the calculation, to see if you still meet the goal and the scopes. And in that phase, at least you also describe the life cycle impact assessment methodology. So which are the impacts you're interested? Is it only global warming, primary energy, or also human toxicity or biodiversity? This really is part of the goal and scope. And as I've mentioned before, you really decide on the impact you're really interested. And later on in the next lecture, you will also see that maybe not all of these impacts can be assessed um, with the same accuracy, with the same certainty. There are some more uncertainties if you talk about toxic, human toxic, human toxic, human toxicity. No, that's it. Human toxicity or greenhouse gas emissions. So in the assessment methodology, there's still a little bit difference, and we will discuss that. And then from the very beginning, you also have to think, where are all the data coming from? What are the data requirements? Yeah? Even if you start to build up your unit processes, you have to keep an eye which data are really available. Um, for example, you can say that the bioethanol production is only one unit process. Over the all bioethanol production is one unit process. But if you want to analyze different pretreatment methodologies because you want to compare them, you have to split up the bioethanol facility. At least the pretreatment should be a separate process for which you need the data. Then you can compare different pretreatment options. Yeah? So the goal and scope at least also defines to which degree of detail you have to put and set up the modeling. Yeah? And so this sounds all a little bit theoretically, but at least you really have to consider and be aware that finally you get the answers for the questions you ask. And in the goal and scope, you formulate more or less the key questions, and only these questions then can be answered. Yeah. And if you need another question, at least you need a different goal and scope. Um, Coming back to comparing a system using bioenergy, and we compare it to a reference system using fossil energy. So again, this is in most of the cases comparison ethanol to gasoline, coal power plant to, to maybe energy made from wood chips, and they all provide an energy service. And it starts with the collection of residues, if we use residues, or with the cultivation of biomass in agriculture or in forestry, transport of the feedstock, processing to a bioenergy carrier, distribution of the bioenergy carrier, and the use of the bioenergy carrier. This is at least the main 4 to 5 processes that are relevant for a bioenergy system. Secondly, if you compare it to a fossil system, it looks relatively analog. You start with a fossil resource, you extract it. Yeah? So the extraction, then you have to transport it, you have to process it to a fossil energy carrier, you have to distribute this energy carrier, and you have to use this energy carrier. So you see there's a relatively good analogy between the bioenergy system and the reference system. But as we know, especially for the bioenergy systems, we might have co-products showing up. Yeah? So it might be in the processing to a bioenergy carrier from ethanol, from grain to ethanol, you produce animal feed. Yeah? And then you also see here you have a co-product. And so your system, bioenergy system, gives you energy, but also product. And to put that in a fair comparison, you have to see on the reference side which product is substituted. Yesterday we had the example of the animal feed. Yeah? So at least you have to see which conventional product are you substituting. So the conventional product is also part of the reference side to make a fair comparison. So this production of the conventional product gives you the same amount and the same quality of a co-product of the product which is deriving from as a co-product from the bioenergy side. Secondly, when you're starting to collect residues, yeah, for example, straw is a residue from grain farming. And the question is, if you don't use the straw in your energy system, the straw will be still there. Yeah, so something happens to the straw, and therefore we call that the reference use. I've heard that here also you burn a certain fraction of the coal because you can't blow in so much straw on the field. So in that case, the reference use here, if the residue is straw, the reference use would be the combustion of straw on the field. And combustion of straw on the field makes some emissions, yeah, particle emissions, CO emissions. So at least on the reference side, you have to include this, because if you use the straw for ethanol, yeah, you avoid the combustion or the burning of straw in the field. So you're really avoiding emissions taking otherwise place on the field, and this is really part of this reference use, which is also part of this reference system. So the reference system, you see, it's not only the pure fossil system, it also includes the production of the products that are substituted by the co-products, and also including what happened to residues if you don't use them for bioenergy. Additionally, when we talk about agricultural land and agricultural biomass, you need a piece of agricultural land. Yeah, if you make grains really only for bioethanol, yeah, you need a certain area. And here again is the question: what would happen on this piece of land if you don't make raw material for your bioenergy system? Yeah? Because the land is there, and if you make the grain for eating and for bread, yeah, of course, then this must also be considered, because then we are lacking of the conventional grain. But at least the area you need for the bioenergy system, this amount of area must be also considered what's happening if we use fossil energy and what's happening on this piece of land. And in some cases, to make it to finalize it, for example, if before on this area you planted grains for animal feed or for food, yeah, this food now must be provided from somewhere else. Yeah, otherwise you're lacking something in this equation, so to say. So on the left hand side, at least you have to consider an additional production of this conventional product, which is avoided or which is substituted by this reference use. It sounds a little bit complex for you maybe on the very beginning, but so the comparison is bioenergy, and you have to compare it on one hand in most of the cases to fossil energy, but some elements, the reference use of residues, the reference use of land, and the co-product also part of this reference system. Yeah? Because they might significantly influence the overall results, because the area is there, the residues are there, and so they are really part of this overall assessment methodology. And to really be honest, to make an LCA for bioenergy or bio-based product is maybe one of the most complex LCA, yeah, because you have to consider so many different aspects related to the bioenergy, which makes things at least complex. On the other hand, this is really state of the art. To set the system boundaries and the elements to be integrated, this is at least at the state of the art to consider bioenergy systems. You always have to care about the residues being used otherwise, or about the area being used otherwise, and the co-products, of course, they're showing up. And finally, I don't know if you heard the term of land use and land use change already. We will, in the next lecture, I will go into more detail on that, because land use change is a tricky thing, because if this area before the reference use was, for example, grassland, and you convert grassland to agricultural land, also emissions occur. Or if it was a forest and you convert a forest to grassland or to agricultural land, you also have a change in the carbon stored on this piece of land, and this is called land use change, and this might also have a strong impact on the overall bioenergy system. and we will discuss that when we talk about the impact category of land use and land use change. Coming back to the technical system, um, this is a conventional bioethanol plant using grains as one source for sugar, coming here from the left-hand side, and from the top you see direct the sugars coming from a sugar plant, and these are the main elements um, you to produce at least the bioethanol and to produce the animal feed with the key processes. And in that case, you also have to at least consider how many sub-processes in your bioethanol system you have to model. At least the drying and the pelleting is only relevant for the DDGS. Yeah, so at least the emissions and energy carriers used for this are only relevant for the DDGS and have at least nothing to do with the bioethanol. This is a reason why you really have to consider them separately, because these emissions are not to be allocated. Whereas the fermentation, the raw material cultivation, the the distillation, they all need an allocation, because in that process they are common for the bioethanol and the animal feed. And therefore, it's sometimes you have to split up the processes following the general recommendation from the ISO norm to avoid allocation. And if you find processes in the overall system that do have only one product, you should separately define them in the as a unit process. This is another production of bioethanol, um, because we have studied many different bioethanol facilities in Europe. And for example, they have a first step here. They use the bran from this wheat based bioethanol production, and in the first step they extract the bran, because they use the bran as an energy carrier. So they burn the bran to to um, to provide heat and electricity to the bioethanol facility. And that, of course, has to be considered when you think about the covering of the energy demand of the facility, if it's coming from bran in this specific case, or is it coming from natural gas or from straw or from any others. So at least it's really a technical approach on the very beginning to understand the technical process, the different flows, and the main unit processes of the system. Um, Further on, when we talk about modeling of life cycle assessment, there are in principle two different types of life cycle assessment. One is the so-called attributional life cycle assessment, and the other one is the consequential life cycle assessment. Most of the LCA nowadays are attributional LCAs and not consequential LCAs. The main difference is the attributional LCA at least is when you're considering one bioethanol plant. Yeah, so only one plant, and compare it to the overall system, because one plant would not change the overall system significantly. Yeah, so for that you do an attributional LCA. The consequential LCA would mean if we really build many bioethanol facilities, because we really want to substitute maybe 20% of the current gasoline demand. Yeah, so you really need many bioethanol plants. You need much more feedstock. Yeah, and this might have additional effects in the consequential LCA, and effects that are much more complex if you just add a little bit. Yeah? And so, but still, maybe for you, it's in most of the cases, I assume it will be attributional LCA, and because consequential LCA has normally as a starting point also different scenarios for the years to come, to see how much bioethanol or additional wind energy or others is really needed in the future, really big amounts, and these big amounts really change more in the overall system compared to the attributional one, which only incrementally changes the overall system, so you can more or less consider it isolated. This is just relevant to that you remember there are two different types I assume in most of your maybe future applications you do an attributional life cycle assessment. And at least what I've mentioned in to the slides before is written down here again. It's especially here the definition of the reference system when you consider a bioenergy system. So this is really the most challenging area to define an adequate reference system, which is on one hand fossil energy, but still covering the land use, the reference use of the residues, and the reference production of any co-products. Um, Number 6 is relevant, the changing of carbon stocks, which is part of the inventory analysis, especially when you convert one land use to another land use to produce bioenergy carriers. Yeah? So if you convert grassland to agricultural land, you have a loss in carbon storage on the soil. Yeah? And even with your agricultural practices, it might be that you change the carbon content of the soil if you do a more intensive agriculture or a more extensive one. So the changing in the carbon stocks is also relevant to see if more or less carbon is stored per hectare, because the difference of the stored carbon is on one hand the CO2 emissions or an additional CO2 uptake that has to be considered in the overall comparison. We've heard already yesterday different units, functional units, when you compare different systems. Yesterday, I mainly talked about electricity driven kilometer, ton kilometer, passenger kilometer. In LCA, you call them output related functional unit. Yeah, that tells you that the product, at least all the impacts, are allocated to the driven kilometer. So much greenhouse gases per kilometer, so much greenhouse gases per ton kilometer. In bioenergy LCAs, there could also be a different question asking, okay, I have a hectare of land. What's the best use of this hectare of land? Yeah. So they say, okay, if I use on this hectare of land, make maybe grain or sugar cane, if that is possible from the climate, to see what has higher or lower impacts by making different products. Or in forestry, I have a tree and I want the most sustainable use of that tree. Yeah. And so this is on the very beginning of the LCA. So it's called an input related functional unit. And then you get a result that per ton of wood, you might save in case 1, 10 tons of CO2, and in case 2, only 5 tons of CO2. So these systems might produce different products, but the question here is, what is the best use of a piece of biomass, or what is the best use of a piece of land, yeah, to plant there? So this is a different question that should be asked in the goal and scope. From the LCA point of view, it's a so-called input-related functional unit. And this is very often the case when we talk about residues. Yeah, you have 1 ton of straw or 1 ton of used cooking oil. So what's the best way to use this material? Should we make biodiesel or should we do something else? And that is at least relevant that there's also an input-related functional unit if you have a question on that. The background for that is because biomass is limited anyway, yeah, because we don't have, it's regrowing, but it's not endlessly available. So therefore the question, what is the best use or the most sustainable use of a piece of biomass or a piece of land, is quite essential. Yeah? And so that's important that I have also mentioned this type of input related functional unit. Also, when you do an analysis of bioenergy for different impact categories, if you know already in advance what might have a strong influence on your results, if you know that already from literature or other studies, that's very good, because then in your modeling and in inventory analysis, you can be already quite precise in these elements. You know they significantly might influence the results. And that's why I show you here some key factors. We know already what is relevant when you make an analysis on bioenergy. And one is, of course, the feedstock procurement or the feedstock cultivation, logistic, and supply. That has for sure a significant influence. And we know also that the changes in the soil carbon stocks in biomass and soil is essential. So if you build your system and make the inventory, at least you should already include from the very beginning these carbon stocks in the system. Otherwise, when you then calculate and you're on the very end, you have to go back again and maybe make a more detailed um, analysis. Secondly, it's the environmental impacts of agricultural residue removal, because you have to collect them, you have to process them, and we know that might have a significant influence. We heard it also yesterday from Professor Singh in the presentation from comparing bioethanol plants and production systems. So this is a quite relevant part. And thirdly, in agriculture, the N2O emissions and the methane emissions are quite relevant. Methane emissions are mainly relevant for animal housing, manure management, if you're looking towards biogas and biomethane. The N2O is a more basic thing, because all agricultural systems, they need nitrogen as an input. Yeah? And as soon as you put nitrogen on a field, there is a specific mechanism I show you in the afternoon in more detail, directly producing N2O emissions on the agricultural land. Yeah? You cannot avoid that. You can minimize it a little bit, but we know that the N2O emissions from agriculture are quite relevant. So considering the nitrogen fertilization and the N2O emission in agriculture in the inventory analysis is, we know this is relevant, so you have to be very the necessary detail to really reflect this effect. Of course, the second part is, all the time you convert biomass into something else, you have a certain efficiency, yeah, because you never can convert it by 100%. So this overall feedstock conversion is totally relevant in all of the processes. Even this conversion to your main product might be low, but maybe to the co-products it might be higher. But at least considering really the conversion efficiency to useful products, that is a really relevant thing you should already consider in the modeling. Status of technology. Of course, there are different technologies. You define in your goal and scope which year you're doing your analysis, and normally for this year also the state of technology for this year. So if you make an LCA for a future technology, you also have to assume specific things for future technologies, which is especially in an emerging area like lignocellulosic bioethanol quite relevant to specify the state of technology in future, because it's not commercially available today on commercial on bigger scale. So you have to assume and describe especially the status of technology. And again, here we call it the fate of co-products, at least to consider all the co-products in the necessary details. Yesterday already, Professor Singh mentioned the fore and background data. At least the main difference is the foreground data, at least in these unit processes you do specifically analyze in your LCA. They need mainly foreground data. They are project specific. At least you know the details of a certain pretreatment for ethanol. You know the details of a specific vehicle. So these are the foreground data, very project relevant. So if I visit the bioethanol facility, yeah, they have to tell me what is their steam demand, what is their electricity demand, how much raw material grains are going in, what is the water content of the animal feed coming out. All these technical data of the specific system, they must be taken from the specific system as far as available. Yeah. Secondly, if they need electricity and they tell me this electricity is coming from the Indian electricity grid mix, for example, yeah, then I can say, okay, the electricity generation in India, that is more or less a background data, because in databases you find information how electricity is generated here, and maybe you find the information. So normally in your LCA, you go in the database and take this information, and you don't have to model the overall electricity supply from India. Or if you need natural gas or you need gasoline in your process, of course you can look on databases. Um, but in detail, when you once run through the LCA, it might come up on the very end that you see that the background data has a significant influence on the final result, for example, electricity emissions. And therefore, it might be that in the second round of this iterative process, you have to maybe look more in detail on the electricity supply. Yeah? And then it might be that a background data becomes a foreground data. Yeah? So it's really an iterative process, but that has to be um, considered. Here's an example of the of typical foreground data. If you look on a vehicle system, it's the type of fuel, it's the vehicle mass. So if you look on a vehicle, you have to describe the vehicle properly, and this is the example for the foreground data, and this is the one example for the background data, um, which you normally take from different databases. I will show you tomorrow the available databases, which are relatively easy to get access to. Normally, it's electricity mix for electricity you need for the different processes. It's also the production of specific materials. So in the building phase, the concrete, the steel, the aluminum, the copper, you need to build your system. Normally, you go to a database and use that. Even if you need chemicals, different chemicals, you normally take them from a from a database. But the main distinction, I would say, is really in these unit processes, these 5 or 6 you define in your system. Most typically for them, you need really the foreground data. And um, from my experience, I know that the biggest challenge and work is really to get all the data for these systems. Yeah. Normally, I would say 70% of the work is really in collection of the data to get appropriate data. Normally, you collect this data per year, which is a relatively reasonable. See what's going in per year in and what's coming out on one hand, but secondly, you really need all to get all the data in the right units. Because in most of the time you don't have all this data by yourself, because you have partners that provide you the feedstock, you have partners that do the transport for you, or the others are running the bioethanol facilities. You have to communicate with them, find a common way for communication, and really collecting the data needs you. I would say 2/3 of LCA work is collecting data and write data and data quantification. Yeah. If you once have them on the right form in your calculation tool, the LCA is the calculation of the impact is at least goes quicker, and this is less work. Yeah? And you always fall back on the principal data from the inventory, and when you have the results, at least you always look on the input data you've used, and to really make sure that the results are correct. I jump over this. Here you see just a key summary when you compare a bioenergy system and a reference system with fossil energy. I won't go through the details here, but it gives you at least the key parameters you need for the different processes. So in the first column, you see here the land management. This is the cultivation, the transport, the condensation, the distribution, the use, and the disposal. And this table tells you what are the key parameters you need to describe this process. So this is a very good starting point when you look on the bioenergy system to see which parameters are really needed as foreground data to describe my system. And similar also on the reference side, also the key processes in the first column of the fossil energy system, and also giving you the key parameters. Maybe there are 20 or 25 main parameters if you want to calculate greenhouse gas emissions and primary energy demand. You're interested. So if you only look on greenhouse gases and primary energy, you need data describing that. As soon as you go to other effects, yeah, emissions to water, other emissions to air, the list of data and parameters you need even becomes longer. And it could become very long if you want to cover all these 15 impact categories. They have, I would say, hundreds of single substances behind them in the inventory analysis. Yeah? So this is an incredible work to get all these data. Yeah? And sometimes you don't get these data, for example, for human toxicity. So many substances are bad for us, bad for our health. And at least if you want to assess human toxicity, you need to collect all these data in the inventory phase. Yeah? That you once describe how much of these emissions are coming out before you start your assessment on the human toxicity. Yeah? So this also is at least a criteria for setting the goal and scope, and very often you really have to limit the goal and scope to very selected impact categories. Yeah? Because otherwise you're really lost in the need of many different data. Okay, I'm coming back for just to give you the the procedure how to do the inventory analysis. Again, I'll show you relatively briefly on an example. The system description, the key characteristics of the technology, the mass and energy balance. Cost and revenues is in gray because that is not relevant for the inventory analysis. It's more having in mind also that this system must somehow have a business possibilities. Yeah, if it's so far away from any commercial application, but it's not part of LCA because LCA has nothing to do with money, nothing to do with euro, with dollar, with rupee. No, it's a pure technical unit. Then the different value chain, the definition of the reference system, and of course the key characteristics in the impact assessment on the greenhouse gases. Again, you've seen that yesterday, so I can be quick. Still, you can use this definition of a biorefinery. We've learned yesterday to describe the key processes in this uniform format. You're giving the key parameters, which are all foreground data, describing at least what are the products coming out. In that case, we have 3 products coming out, and we have a long list of different inputs, auxiliaries, many chemicals, electricity, heat, and so on. And especially what is the key feedstock in that case? It's corn stover, more than nearly 900,000 ton. It's an example of a biorefinery we analyzed in Australia. So at least again, it's the mass and energy balance that is quite relevant. And here also we calculate the efficiencies because the conversion efficiencies are quite relevant. Conversion efficiency in terms of mass. So how much of the mass ends up in the product, how much of the energy input ends up in the product already gives you an indication of the overall process. And these are some at least simple parameters, but at least you have to get the information from the one who is running these facilities. And then you make the mass balance and you make the energy balance, and that this already gives you an indication where you have to be in your modeling and data collection more detailed, and where you can be maybe a little bit rougher, so to say, because you know that maybe the chemicals or some specific inputs might be not so relevant for the overall system. Um, the costs and the revenues, I always like to bring it a little bit in the picture, because the commercial system is very relevant, because sometimes people are very optimistic on the technical side and saying, if I apply all the sophisticated technologies, I gain the highest environmental benefits, which is true. But on the other hand, if they are so far away from any economic application, of course, then it's not really realistic. So you create an LCA which gives you good results but has nothing to do with reality. So it's always a little bit grounding yourself to the reality, and reality is not only environment, it also has a strong economic component. Then again, we've seen yesterday already a picture on that. It's the same, this biorefinery fact sheet. I really can recommend, when you look on the biorefinery, if you use really this fact sheet, it's really a good way to condensate the key information on the biorefinery for the LCA, and it's a very good instrument to also communicate the results then to others, to stakeholders, and so on. And it's at least the key basis. When you have once defined the reference system, you can start calculating the greenhouse gas emissions and the primary energy demand in a relatively uniform way. And these are at least the results. We will see later on this primary energy. I already mentioned several times. It's very important to distinguish the fossil part of the energy and the total energy, because the difference is always the renewable energy. So some studies only focus on the fossil energy. Um, I think it's more relevant to have the total energy in, and then distinguish between the fossil part and the renewable part, because if you don't include the renewable part, you get not an information about the energy efficiency when you convert your biomass to something, if you only look on the fossil side. Okay. Finally, my last 3 or 4 slides is uh, a recommendation for most of the LCA work you do. Um, as I've mentioned yesterday, LCA is still an estimation on environmental impacts, and you need many assumptions, key data, foreground data, and a very necessary key to all of that is to be transparent. Yeah? At least to really make it clear. Documentation in the biorefinery fact sheet is one thing, and in the overall reporting, and this is really a big challenge. Scientists normally are able to really describe in detail what they are doing, and this is especially for LCA a quite relevant thing. And I've shown you here one example. Um, we are doing together with Green NCAP, that's an organization in Europe. They are testing vehicles. They are testing different vehicles, how much energy they need, electric vehicle, hydrogen vehicle, conventional one. They do the testing. And we did, together with them, we developed an LCA to assess really all the different vehicles on an LCA base. Yeah? And as there are so many different vehicles with different materials, um, the key element was that we really made a very transparent, comprehensive reporting, putting all the main data in a report. Because when you once published that, and this was published, and we published in this database on the internet, you find here, we have roughly 30,000 different vehicles in there. Because it sounds a little bit stupid maybe, but in Europe you can buy 30,000 different vehicles. Even from one brand, they have more horsepowers and less horsepowers and different features. So there are so many different vehicles, and we calculated for all these 30,000 vehicles a specific LCA, especially for consumers who want to buy a new car. They have the possibility to find possible cars there and make an LCA based comparison that looks maybe like this. Here we compare three cars on the greenhouse gas emissions and together with their primary energy demand. And even that, um, if you put such data on the internet, many people look on that and have ideas and say you've done something wrong or you should do it the other way. And if you really have a transparent documentation in a report, yeah, people, you can always say, look, we have this information here, we have this information here, this is our assumptions, and for us it's also a good instrument to learn, because you always make sometimes some bugs or make different assumptions or whatever, and the more transparent you are, the better the discussion is. And even if we make a bug there, I don't care, let's change it and recalculate it, and then we have a new result. If you're not so transparent, maybe you don't find bugs in the overall system. So really, transparency is very relevant. The main application for this LCA is really, you see, these are all the same cars, and you can buy cars that have in the total life cycle nearly 60 tons of CO2, but there's also one only having half of the emission. Yeah, so even for the consumer, the information is quite relevant. When you buy a car, you have a possibility to choose what's the car you're interested in. And this is also, for me, a very nice sign that LCA is really entering our daily life. You've seen the milk package yesterday, and now the discussion on purchasing a new cars. There's also information provided on the LCA level. And finally, I also applied this program for at Ioneum research. We have roughly 15 different business vehicles at Ioneum, and we have vehicles in total. They are only having 17 tons of CO2, and we have vehicles having 90 tons of CO2 in their overall lifetime. Yeah? And I also use this information to discuss inside Ioneum. Maybe in future we should have this more in mind. Yeah? And maybe buy cars that are maybe smaller, but they have significantly less emissions compared to others. Yeah, so at least this information it has also a quite practical relevance. Um, to be honest, very often these business cars are not bought because they save the environment. It's still saying you need a big car if you're representing a big organization. But anyway, it's really a starting point, and the difference is so big. Yeah? It's 17 ton is one vehicle, and we really have that in our fleet. So the best is only having 70 tons, and the worst is having nearly 90 ton, and this is a factor 4 or 5 in in between. So this is again um, finally to be transparent and to use this information also in practice. This is my take-home message for this morning session. When you do the life cycle inventory, it's the description of the technical system. This is very important. It's all about technology. You have these unit processes. Normally in your system, you have 4 or 5 unit processes. That will also be the group work we're going to do together with you. These unit processes, when you build it, when you operate it, and when you dismantle it, this is the information you need to reflect and start analyzing the environmental effects. It's all about mass and energy balance. You only use here physical units. I did not mention that so precisely before. In the inventory analysis, you really have physical units. You can measure everything. The mass, the liter, the concentration of CO2, you can measure everything. Whereas in the impact assessment, you cannot measure CO2 equivalent in the atmosphere. You can measure CO2, but you cannot measure CO2 equivalent. This is a big difference between the inventory and the assessment in life cycle assessment. And last but not least, be transparent. Really put all the things in transparency. I say it's relatively easy because you just make tables with the key data you need for your systems, and in a technical environment or a natural science-based environment, giving tables and diagrams is at least a way for transparent documentation. Okay, that was it for this morning. Thank you very much for listening. And if you have any questions, I'm ready to answer them. More light.
So thank you, Dr. Gerfred, and it was very interesting to note down that at Yonam you have prepared the LCA analysis of so many vehicles. Though the car company they might not be liking it very much because the environmental environment concerned people they might you know uh, think about changing their vehicle keeping in view your data. And the same thing, I think we don't have any data available on this aspect here in Indian industry, I think. So definitely it will affect the decision making of the prospective car buyers, and it may not be good for the industry, but definitely those who wish to be environmental conscious, they should be they should have this data at least with them. Yeah. So any question, participants?
Maybe I can answer this
Uh-huh.
or comment
Yeah.
your first. What does the automotive industry think
Yeah.
about our
Yeah.
results? One thing is we've done this for the European market, but we have also started to extend that to other countries. Yeah, and we have also been, not me, but the colleagues from the Green NCAP, also with colleagues here from India, and we have also South America. They also apply the same program, but they have different vehicles covered there. And this is one thing. And the other thing is the car industry um, are split in two parts. um, the ones complaining, they say my data are better than the one we calculate. Yeah, and we say okay, that's fine. Please give us your data. Yeah, and then they say it's so complicated. But we are currently in the process to get more brand specific information from those who are complaining that our figures are too high. Yeah, the other half. Yeah, we now know we have a little bit underestimated the effects, especially on the production side. Yeah? So they do not complain because they perform better in our database than they really are. Yeah? And so they do not complain on that. And one example I can mention it was Volvo, yeah? Because Volvo now published their own LCA, which gives you really higher emissions than we have because the automotive industry now is forced to provide LCA information stepwise. And there's currently harmonized the methodology for the car producers. And they really have to report public reporting in, I think, in 2 years. I don't know exactly, but they are also forced to at least publish LCA results on their specific vehicles. And Volvo was one of the first now publishing them, and they have significant higher emissions than in our system. So it depends on the result. If we overestimate, they complain. If we underestimate, they are quite happy.
Yeah, there was some case in US also. I think Volkswagen they were penalized by US government on these emission issues, I think.
Yeah, on the NOx emissions, that was a big issue. Yeah.
Yeah. Great. Yeah. So good.
Good morning, sir. So as you said that different we should use the cars with less emission. So in that case, India is a vast country. We have mountain regions, we have plain regions. So the car we choose also depends on the power, the cubic engines, CC value we say. So how can we apply an LCA for the different parts? Like it's a mountain region where more powerful cars are required. And now we are on the plain region. So how can we compare the plains, the different plains? The areas, the mountain areas and the plain areas with This because the same car which will be using here can't be used there. The emissions are less. We can use a light car over here, which is not so powerful. But in the hilly regions, we need a powerful vehicle. So in that, what might be the case?
Yeah, a very important question. Yeah, at least in all these vehicle LCAs, the key question or the main influencing parameter is really how much energy do you need per kilometer. Yeah, and this not only depends on if you're going up and down or flat, it also depends if you drive or I drive. Yeah, either the driver influences, yeah, and the speed. So the influences on the energy consumption is extremely high, extremely high. So in this big analysis, we used the testing cycle. There is a testing cycle which was developed and changed in the past several times, and now they have a testing cycle also all car producers must fulfill, for example, the NOx emissions. And this is a procedure on the test in the lab where you drive high speed, low speed, up and down, braking, stop and go. So different driving events, so to say. They are a cold start and hot start, and the sum of these emissions is at least a criteria that you're allowed to bring that on the market. But still, this is a value somehow artificially created, but really trying to reflect more and more reality. Yeah? And and still, in that case, finally, if you want to know it in detail, you really have to do the car testing with going up and down. And one interesting thing is really this green NCAP. It's really fascinating. The green NCAP, they're testing the vehicles and they're testing it under the average conditions and under worst conditions and under optimal conditions. And they described it very well also on the web. And the difference is extreme. Yeah? So a difference of 50% more or less energy consumption, which gives you significantly more or less greenhouse gas emission. It's really a reality that these vehicles perform so different. Yeah? And the green NCAP, they really tested under harsh conditions. And in that program on the internet, we have also for the tested cars, not all 30,000 cars are really tested by green NCAP, but the ones are tested roughly 200. You find both values for the best case, for the worst case, and the average one. And you see, and there you can see really big differences. Yeah, yeah. And that's so.
So many of the participants must be thinking that it requires a lot of data.
Yeah.
Like in case of bioethanol, you need data on soil, how soil carbon is affecting. You need data on fertilizer applications. You need data on other aspects. So from what is the primary source of data? Or some databases are there where we can have standard values?
Yes, I will talk tomorrow about the databases. Yeah, it depends with whom you do the project. Yeah, in that case, we got the vehicle data from Green NCAP and our partners in the mobility clubs. They provided us all the vehicle data we needed. Yeah, and all the other data came from our data pool we have developed at Ioneum Research. If you do it with an existing bioethanol facility, of course you need the operator of that, and then you also need the farmers that tell you what is the yield, what is the water demand, what is the fertilizer demand. So at least you need the partners for existing facilities. If you are doing for something in future, lignocellulosic, you have to find the different data and reasonable applications or modeling sometimes also to really describe the mass flows and energy flows. You think this describes the technology in future. Yeah? So it's really a mix depending on the goal and scope where you get the data from. And many of our clients, when we make them an offer for doing an LCA, we also give them already the tables. We say, but these tables you have to fill because we don't know it. Yeah, so we get the directly from our clients, and they also need resources on their side to collect all these data. Yeah? And this is really, as I mentioned before, I would say 70% is really data collection, ending up really with the right units. You know, that's a typical bug you can make if you have the megawatt and the kilowatt hour somewhere mixed. That happens. So this is really the biggest effort to get the data. Yeah. And finally, in your result, you do a sensitivity on the parameters that influence results the most. So you can also say how stable the results are.
Yeah. Thank you. Anybody else? Okay.
There's one more.
Good morning, sir. Sir, about the inputs and output, I came to the conclusion that input should be higher than the output. So that's my conclusion. What's your comment?
No, normally not. So
It's
at
not.
least all the material that goes into a biorefinery must come out again in form of products, co-products, or releases, so that the mass normally is not lost. No, no. Sometimes that's also tricky to really make the closed mass balance, but at least in this calculation, you can also say if you don't know exactly where it goes to, then it's called unknown, but the mass balance should really be closed. Yeah, yeah.
So it should be in equilibrium.
Pardon?
Sir, it should be in equilibrium.
Yeah, yeah.
Inputs
It should be an equilibrium. Yeah.
Okay, sir. Thank you.
Yeah. And that's really tricky to make a closed mass balance for the key processes. Yeah. Okay.
Okay, we will have a break for maybe 30 minutes now, and then we'll meet after tea.